Well, I'll say good morning to everyone. It's nice to see a nice pile of homework here. Give me something to do over the holiday weekend, I guess. So, last class we were talking about spherical waves and how to write the wavefront for a spherical wave. And we said that if we had a spherical wave with a radius r, we could write the wavefront distribution as x squared plus y squared over 2r. This is a parabolic approximation. And if we have then a shift in the image position of epsilon sub z, longitudinal shift, then we have a wavefront here that goes as epsilon sub z, x squared plus y squared over 2r squared. And if epsilon sub z is positive, then this is a negative quantity. Or if we were to increase the curvature, increase the OPD, then the epsilon sub z would be negative to make the result here positive. And then we could have a tip and tilt of the wavefront, so we have a lateral displacement. And if in the x direction it's epsilon sub x, then we could write the wavefront there as epsilon sub x times x over r. And again, if the OPD is positive, then epsilon sub x must be negative. And the same thing for epsilon sub y. So epsilon sub y times y over r. So this was still a perfect spherical wave, but we might have a little defocus, we would call that, or a little tilt in the beam. Well, before we go on and talk about angular, transverse, and longitudinal aberration, I wanted to go through a little diffraction calculation going back to 505. And maybe I better make it a little smaller. So I'm going to say I have some pupil here that has a radius, or I should say a diameter of 2a, radius of a. And it's coming, the beam is coming to focus over here some distance away. I guess for my drawing I write this as f. And so we could write the Fresnel diffraction equation for this, which all of you have seen. Probably the print's a little small to see from the screen here. But there's a factor out in front that we're going to sort of forget about in just a minute here. And then inside we have the wavefront and then the Fourier transform of that wavefront. And we could say that we have a pupil function here where the phase in the pupil function is measured relative to a reference sphere of radius f. And so we're saying we have a sphere coming to focus here, and then we have some phase distribution across here, and some aperture here, and we'll write that as the pupil function. And we're not going to worry about the factors out in front here, so I'll just write that as c. And we're going to calculate not the amplitude, but the irradiance here. So we'll take this and multiply it by its complex conjugate. So we have the Fourier transform of the pupil function, whatever the pupil function is. We'll worry in a second here just what that is. And if the aperture is circular and radius a and illumination is uniform, and we're going to normalize, so for no aberration, the peak irradiance is 1, then we can simply write this as 1 over pi a squared times the pupil function here, Fourier transform of that. Now the pupil function, which is what I want to think about now, is we're going to say we have a circular aperture. So that's the way I write circular aperture. And then we have e to the I phase. And this phase describes the phase distribution corresponding to the aberration across the pupil. And so if the only aberration I have is defocus, then this is just some quadratic phase factor here. And so I can write this as e to the I pi, or e to the I m. M is some number. It may be an integer, it may not be an integer. E to the I m times 2 pi. And then we'll have the square of whatever coordinates we're using in the pupil plane and normalize that, dividing that by a squared. And if we write this in terms of a Hankel transform, which is nice since this is rotationally symmetric, and so we can use a Hankel transform. And so this is just the absolute value of the Bessel J0 of pi r rho, and then e to the I m 2 pi rho squared 2 rho d rho, and then quantity squared. So we can then calculate what this looks like as a function of defocus here. So again, the defocus is m, some number, times 2 pi times, well, the rho squared, where m then would be the number of waves of defocus. So we can calculate this. It's not too hard to do, and I did it using Mathematica, but you can do it however you want. And I don't know how well, can you see that? Maybe I'll turn the lights down for a second here. I don't want you to go to sleep on me, though. Does that make it a little bit better? So what am I looking here? So this is the angular, so the light's coming down to focus here. And if I were to look at the focal plane, it would just be a plane right through the center here. And so in this direction, this is the angular distance, so I'll write as units of lambda over d. And so this would be 2468 lambda over d and so on, out in this direction. And then along the x-axis, I write the waves of defocus. So for m equal to 1, that would be here, m2, m a half, and so on. So that's just the irradiance profile that I see going through focus. So before I go on, do you understand what the plot is? Have you seen a plot like this before? Okay. Kind of looking here, looks, well, this is be our airy disk if I just draw a plane this way and I look at the center portion here, and you can see where the first zeros are. But if I go along the axis, I see something kind of interesting here. That looks awfully dark. In fact, that's a 0. I don't know how well you can see it on the screen. I can see it very well on my computer, though. That's another 0, and so on. So along the axis here, I see I have 0 at 1 wave of defocus, 2 waves of defocus, 3 waves of defocus. That's kind of interesting. So as I bring the light to focus and then I move along the focus and I look on axis, I will see I get a maxima here, and then I get a 0, another 0, another 0, and so on. I'm getting these zeros at 1 wave of defocus, 2 waves of defocus, and so on. In fact, there's going to be any integer waves of defocus, I will have a 0 right on axis. That's kind of interesting. I mean, it falls out of the math here if you go through it. But can we kind of think about this physically? What's happening? What's causing these zeros on axis? Everyone here knows what a Fresnel zone is, right? And if you go across a Fresnel zone, how much does the OPD change by? Half a wave, right, okay. and the areas of the Fresnel zones are equal. So if I have one wave of defocus, how many Fresnel zones do I have? Two Fresnel zones. And I go across each Fresnel zone, and the OPD varies by half a wave. And so if I have two Fresnel zones, in each point in the first Fresnel zone, I have a point in the second Fresnel zone that's out of phase by 180 degrees. And so these two Fresnel zones are canceling out one another. So on axis for two Fresnel zones, I'm going to have 0 radians. If I have if I have two waves of defocus, now I have 4 Fresnel zones. And first one and second one cancel each other, third one and fourth one cancel each other. And so once again, I have a 0. And 3 waves of defocus, 6 Fresnel zones, cancel one another out. If I have a wave and a half of defocus, now I have 3 Fresnel zones. 2 of them will cancel and I'll be left with 1. So I'll get, more light there. So for any integer number of waves of defocus, you're going to get a 0 on axis. Okay. So that sort of explains what's happening here. I always thought this pattern, again, I don't know, you don't see it so well on the screen as I can see it on the computer and as you will see it in the notes. So it's kind of a pretty pattern. The next plot, I don't know. Once you get this stuff in the computer, you just have to play. That's just a contour map through focus. And I don't know that it really shows anything that we don't show up above here. Now, geometrically, I wouldn't have all this structure in here. And in fact, geometrically, what I would, forget about diffraction, I would just have a cone of light coming in here, coming to a perfect point, and cone leaving. So let's be nice if on this diffraction pattern, I could draw what the geometrical cone of light looked like. Now this was a little more work for me, but I think it works out pretty well. So I want to draw the geometrical light cone on these plots. So we say that delta W defocus we had from last class, it's 1/2 or minus 1/2 epsilon sub z, and we'll write this here as a over f squared equal some number of wavelengths. It may be an integer, it may not be, but anyway, it's equal to some number, 1.43627 waves or something. Okay. And so, forgetting about the minus sign here, I could say that epsilon sub z is 2 f over a. So f, remember, f was the focal length, or the distance away that the light's coming to focus, maybe I should say, divided by the radius of the aperture. So it's 2f over a squared m lambda. The tilt here, well, tilt from last class, we can go back and see that it's 2a y over f. And let's say that's equal to n lambda, or n is some number, okay? And so y is f over a, n lambda over 2. So n is the number of waves of tilt introduced across the pupil diameter for a lateral displacement of y. So if I want to draw this geometrical cone, what I'm going to do is I'm going to take the ratio of this y here to epsilon sub z and just calculate it here, and it turns out to be a over f, n over m 1/4. Or I can write that a over f is 4m over n y over epsilon sub z. Now A over F here is a, 1/2 the cone angle of the light. And so I can draw the geometric cone angle of the light as long as the lines I draw satisfy this equation here. So if I make n, well, I could make these 0, okay, so that would be the center point. I could say make n 16 and m4, then I'd have 16 over 16 or 1. So I'd have A over F as y over epsilon sub z. So that would work. So that's what I've done right here. So I've just drawn these lines. So geometrically, I mean, I think this is pretty cool, actually. Geometrically, then, what I would have would just be light coming down to the cone here, perfect focus, and coming out here. But what I get from diffraction, I mean, I get this structure in here. I get some type of interference pattern in here. I get these zeros along here. And the light doesn't come to a point there, but it's spread out here. Now, if I want to change the F number of the system, all I do, I take this pattern here, I can stretch it either horizontally or vertically, and I stretch the pattern, I stretch the lines, and so on, and I might get something like this. So that would be for a slower system here. Diameter of the pupil is not as large as it was up here. Okay. That's, I don't know, always thought that's kind of cute to look at. Well, let's see. I mean, we have this data in the computer, calculate these crazy Hankel transforms. I could draw out the contour maps, but they're, I don't know, nothing much there that's not in the previous ones. Or I can draw the 3D maps here. This is showing what the radiance looks like as we go along focus. So this is going along focus in this direction, and then this would be the transverse direction. That's kind of cute. I'll rotate it a little bit. About that. So these would be the zeros. And I don't know, do I have any more? Yeah, another one here. Okay. Any questions on that? Okay, so we've talked about spherical waves quite a lot. Let's now talk about aberration. So I'll go back here, and then we had just a couple sentences. If I can find it. Okay, so the next section here, we're going to talk about angular, transverse, and longitudinal aberration. So generally, the wavefront in your exit pupil is not a spherical wave, but it's some aberrated wavefront. And so different parts of the wavefront come to focus in a different place. And it's nice to know where these different parts come to focus. So let's zip along here to where the notes continue again. Oops. If I can get this over. Okay, so here's our perfect wavefront back here. Call that the reference. And then here's another wave, which is our aberrated wave. And it may not be a spherical wave at all. So the reference comes to focus right there. This, but at the edge of the pupil here, we have some aberration delta W. To the right, it would be positive. And so this light here, instead of coming to focus there, is crossing the z-axis there, a distance epsilon sub z away, and it's crossing the x-axis down here, a distance epsilon sub x away. And if we look at different points of the pupil here, the rays will cross the axis at a different location, and they would intersect this axis down here at a different location. So epsilon sub z and epsilon sub x are a function of x, y in this plane. And so we can say that this ray is coming down here at the wrong angle. And there's some error, some angular error in that ray of epsilon sub x. Okay. And so we can write here that, not epsilon sub x, but alpha sub x, I should say. And so alpha sub x is minus a partial of delta w with respect to x. And if the refractive index is not 1, then we'll put the n down here, but throughout the course we're going to assume that n is equal to 1. So that's the angular aberration. Before I go on, do you want these lights turned back on, or which way do you prefer, on or off? Okay, good. Okay. I forget, who do we play in football this Saturday? Toledo. A+ for that person. It's the Toledo what? What is it? It's not the Toledo Wildcats, I don't think. What? I don't know, some kind of bird. That's a different. Maybe it's a rocket or something like that, but I don't think it's a bird. But that does remind. Their baseball team. What's the Toledo baseball team called? If you want to talk about birds. That's the Mud Hens. Strangest name in baseball, I think. But anyway, you can check. I think it's the Rockets, but they're not going to be a Rocket this Saturday. Okay. So this is the, and how many are going to the game? Yeah. Well, I better clean my glasses. I'm not seeing the hands too well. Okay, well, hope we don't have any exam questions on the game. So this is the angular aberration of the ray. And epsilon sub x then, if we think here for a second, is just this lever arm r times the angular aberration. So, and I'm going to let n equal 1, so it's just partial delta w with respect to x. So down here we have that epsilon sub x is minus r partial delta w with respect to x. Okay. And a lot of times in optical testing, you end up measuring the transverse aberration. So this turns out to be an interesting quantity here. And you have a similar formula for the angular, both the for y component of the angular aberration and the transverse aberration. So this beam, I want to determine now what epsilon sub z is. So I kind of look at these similar triangles here. I'll go down here. Shame I can't see both at the same time. But we have then epsilon sub z over epsilon sub x is about equal to r over x minus epsilon sub x from our drawing there. And so I can write here, since epsilon sub x is going to be a pretty small quantity, I hope anyway, better be. We can write here that epsilon sub z goes as r over x times epsilon sub x, or the result here is that epsilon sub z, the longitudinal aberration of the ray, is minus r squared over x partial of delta w with respect to x. So that would be our longitudinal aberration. Now, most of this semester, we are going to use normalized coordinates. So x squared plus y squared, square root of, will be equal to 1 at the edge of the pupil. And let's say that h down here is the geometrical pupil radius. So I can write here then, or every place if I'm going to write in normalized coordinates, every place I have an x up in these equations, I need to put in an h times x. So epsilon sub x is minus r over h partial w, partial delta w with respect to x. So that would be a transverse aberration. And a longitudinal aberration would be minus r squared over x h squared times partial delta w with respect to x. So these will be our transverse and longitudinal aberrations. Now, when we get to ways of measuring aberration, we'll find that a lot of the techniques for measuring aberration actually measure either the transverse or the longitudinal aberration, probably the transverse more often. And what we normally want is not the transverse aberration, but we want to know the wavefront aberration. But these are just derivatives of the wavefront aberration. And so we can calculate what the wavefront is simply by going through an integration process of the transverse and longitudinal aberration. Okay. Well, if I talk about wavefront tilt or talk about an angular aberration, what units do I use? Well, it's an angle, and it's probably a pretty small angle. Better be a small angle. You're not going to like your optical system. And so I could use something like arcseconds, or I could use microradians. And does anyone know relationship between arcseconds and microradians? What, 5 microradians is close to 1 arcsecond. So I could use units like that. But instead of that, I like to use some crazy units called waves per radius. Why would I pick such a crazy unit? Well, let's think here for a second. Down here I have some wavefront, like so. And I'll pick some point right here, and I'll draw a tangent to the curve at that point. And I take that tangent line and I stretch it out here across the whole pupil. So this is the radius from 0 to 1. And I stretch this tangent line out, and it goes from, according to my notes, this is minus 11 and a half. And this goes to 0. So that slope right there, well, it's so many arcseconds or microradians or something, but I can say the slope is 11 and a half waves per radius, because this is 11 and a half waves here across the radius. So why would I do that? So the reason I would do that, if I have this pupil and I change the size of the pupil, you know, I'm maybe doing some test setup and I put in an imaging lens to image a pupil, and I change the size of the image of the pupil. If I change the size, these angular aberrations in units of arcseconds or microradians will change. And if I make the size half as large, the angles will double. Okay. And so it's kind of confusing to me that the aberration in units of microradians or arcseconds depends upon the size of my image. But if I use these crazy units here of waves per radius, it will not change. The number of, if I change the size of the beam, the number of waves here will not change. So waves per radius, waves per centimeter will change, but waves per radius will not change. And so I often use these crazy units here of waves per radius instead of arcseconds or microradians. So you'll see that many times during a semester. Okay. So now you kind of understand angular aberrations and transverse aberrations, longitudinal aberrations. Let's now go on and talk about Seidel aberrations. Oh, I guess I did have one more drawing down here. Maybe I should have just shown. That's just a drawing of the wavefront in units. Well, this, I guess, is the wavefront in units of waves. And this is taking the derivative of that, and this is the slope of the wavefront in waves per radius. Okay, so now we're going to talk about Seidel aberrations, and I think you've had that in your other classes. But I want to look at Seidel aberrations, see some properties of them, see what the shape of the wavefront looks like, see what the transverse aberrations look like, and maybe even seeing what if I have a system with Seidel aberrations, see what the image of a point source looks like using that system. So, who first developed the Seidel aberrations? Well, you'd think it would be Seidel. Maybe it was Seidel. I don't actually know the answer to that. But I do know that almost everything, when you find that it's named after someone, that's not the person who did the original work. I don't know why that turns out that way. So I don't know if it was Seidel or not. We'll give him credit for it, but I'm willing to bet it wasn't Seidel. Anyway, I'm not going to go into a derivation of the Seidel aberrations. If you go to Welford's book, or his two books, I mentioned Welford had a first book in 1974, where I think every equation has a typo in it. And then he cleaned that up, and his second book came out in '86, and that's really a good book. Welford goes into a lot of detail on justification of writing the Seidel aberrations the way we're going to write them here. I always wondered, Welford was, he's no longer alive, unfortunately, but he was really a superb person. And how he ever published a book with so many errors in it, it's just like he never proofread it or something. I don't know. That is very, very surprising. So if you have the 74 edition, which you probably don't have, but throw that away and get the 86. So anyway, these are the kind of the terms we're going to talk about making up the Seidel aberrations. And first off, the first term here is just some number, a1 times x squared plus y squared. So I don't know if you even call that an aberration or not. That's a defocus. Okay. And then you have a second term here, which goes as a2 x naught. Now x naught, I didn't say what that is, but that's the coordinate of the, x and y are the x-pupil coordinates, and x naught and y naught are the coordinates of the image. So that's going to be our off-axis location, off-axis image point, x naught. So we have an a2x x naught. So that's like a tilt term. Okay. Then we have a term that goes as a3 x naught squared. That's kind of an interesting term. It doesn't depend upon the pupil coordinates x and y at all. It depends only upon our off-axis point. And so it's like a piston term. And you almost always forget about that. And I think only once in my life did I actually have a need to know what that was in some interferometer we built. But for the most part, you can just forget about the piston term. So we have a defocus term, and we have a tilt term. And whether you want to call that aberrations or not, probably you don't, but I tell you, sometimes a defocus will mess you up. So think of it as an aberration at times. Then we come along here to these other terms, the b's. We have a b1 times x squared plus y squared. And so first off, we see that this is to the fourth order in x and y. Okay, kind of interesting. In fact, there's no x naught here, so we can say it's to the fourth order of x and y and x naught. Okay. And then we have a term here, it goes as x naught, x squared plus y squared. So once again, that's to the fourth order of x and y and x naught here. And then we have a term b3 x squared x naught squared, another term that goes as a fourth order, and a b4 x naught squared, so that's the off-axis squared times x squared plus y squared, fourth order, and a b5 x naught cubed, fourth order, and then we have another piston term here, goes as b6 x naught to the fourth, so it's only a piston term, so we'll probably forget about it. So these are all the b's here are fourth order terms, and we often call these fourth order aberrations. But sometimes in the literature I read these as third order aberrations. And why do they call it third order aberrations? Because if we go back above to our transverse aberrations or longitudinal aberrations where we take a derivative, and so the transverse ray aberrations will be third order because of the derivative. And so you can call these either fourth order aberrations, or it's probably more common they call them third order aberrations. And then if you kept more terms here, you'd have the fifth and seventh and higher order terms. But we're just going to talk about these here as the Seidel aberrations. So in talking about the Seidel, well, right here we're giving credit to Seidel in 1856. I still bet he didn't do it first, but anyway, we'll give him credit. 1856 he gave these formulas. We're going to write these in terms of the exopupil coordinates, expressed in polar coordinates. And so x, if we go back to the way we defined our polar coordinates at the beginning of this section, we have x is rho cosine theta and y is rho sine theta. Okay. So we can, and we normally will write this such that rho is normalized to be equal to 1 at the edge of the pupil. And we often will use the field coordinate x naught to be normalized to 1 at the maximum field position. And so we're going to continue throughout the rest of this chapter. We'll use normalized coordinates. And so we can write these Seidel aberrations here. And what I want to do now is to go through and look at each one of these by itself. And so the third or fourth order aberrations here. And so we're going to look at each one of these. We'll start out with spherical, but let's go down here first and look at the little diagram I have of spherical aberration here. So it's a W040, rho to the fourth. And so the subscript here, 040, 040, what the first one is the field position, the power of the field position raised to some exponent. This is the exponent. Well, there is no field here, so that first one is 0. Second one will be the rho to the whatever power the rho is. Well, this is rho to the fourth, so that will be a 4. And the third one I have to do with the angle theta here, like I'll show right down here. Angle theta, and it will be the third subscript here is the exponent of the cosine of theta. So we'll go through each one of these at a time here. And this is just showing what the wavefront's going to look like, but we'll come back to that in a second here. So starting off first with my favorite, spherical aberration. So spherical goes as W040, rho to the fourth. So there's no field dependence, and it's rotationally symmetric. And so we can write this, it's either rho to the fourth or x squared plus y squared quantity squared. So it's constant over the field, rotationally symmetric. And so these would be contour lines showing what the lines of equal OPD here. And so it goes as rho to the fourth. So in the center, it doesn't change very fast. Remember, rho is normalized to 1 at the edge. And as we move out towards the edge, it's going to change much faster. So contours of equal heights, equal OPDs, are going to get closer and closer as we get out towards the edge here. Now, this light, so here's our pupil back here, and this pupil has spherical aberration. And so all the light doesn't come to focus the same location. And we can say, well, the rays through the center of the lens come to focus way back here. So we'll call that the paraxial image plane. And the rays from the edge of the pupil come to focus maybe here. So we'll call that marginal focus. And in between we have a mess. And there's probably, well, there will be some location here, and we'll kind of worry about that in a minute, but some location where the size of this mess is a minimum. And we'll call that the circle of least confusion. And that would be some distance away from the paraxial focal plane. Okay, so let's calculate the transverse aberrations. And remember, it goes as minus r over h, partial delta w with respect to x or with respect to y. And so if this is x squared plus y squared quantity squared, when you take the derivative of that, so wherever we had the aberration up here. So when we take the derivative of that, we're going to get minus 4r W040 over h times x squared plus y squared. And for epsilon sub y, we'll get the same thing, except this x is replaced with a y. And h is, again, the geometrical pupil radius. And so this is, I mean, the aberration is symmetrical. And so I can write here that the transverse aberration due to third order spherical is just minus 4r W040 over h times rho cubed. Now, the size of this image, so the transverse aberration, depends upon just where I look at it. If I have a lateral shift, or if I introduce some defocus, the size of this will change, just as we showed right here. If I move back and forth here, the size will change. And so I could introduce some defocus here, and from our last class, then we can write that delta W is the spherical, W040 rho to the fourth, plus our defocus term. Defocus term goes as rho squared, and then this mess out in front, which I don't expect you to remember, is epsilon sub z h squared over 2r squared. So this would be the wavefront here relative to a different reference sphere. So it's a wavefront with some defocus introduced. And we're going to see in a little bit that we can actually improve our image quite a lot by introducing a little defocus. And you can see that right here probably, that there's some point where this is a minimum, and we get that by introducing some defocus here. So if that is the wavefront, then I just have to take the derivative to get the transverse aberration. And so the transverse aberration goes to what I had before without defocus, and then the part that comes from defocus here, and so that's minus epsilon sub z h rho over r. Okay. Well, as we saw in our little diagram up above, there's probably some position for which this image, circular image, is minimum. And this image, minimum image, is called the circle of least confusion. And so we're going to introduce some focal shift here for which the transverse aberration has equal positive and negative excursions. And it really corresponds, this may be a homework problem. Sometimes I assign this and some years I don't. I don't know if I did this year or not, but if it's not a homework problem, it might be a problem you want to work out anyway. That this image position corresponds to the position where the ray from the rim of the marginal ray meets the caustic. And it can be shown, this is the homework problem, it can be shown that this image position for the circle of least confusion occurs 3/4 of the way from the paraxial to the marginal focus. And so what you can show without too much work is that if this is the marginal focus, this is the paraxial focus, this minimum least confusion is 3/4 of this distance. And so if that's true, its radius then is 1/4 of the radius at paraxial focus. And again, as part of the homework problem, you can show that this happens when delta W is equal to WO4O times rho to the 4th, and then we're going to subtract, for every wave of spherical, we're going to subtract 1.5 waves of defocus to get to the minimum. If you take the derivatives here, then you'll find out that this will end up being the minimum, I'll say the minimum maximum slope, minimum blur size. So rho to the 4th minus 1.5 rho squared. Well, this diffraction pattern here, I mean, this wavefront is rotationally symmetric. So diffraction pattern is going to be rotationally symmetric. And when you think about calculating diffraction patterns of rotationally symmetric functions, at least I think Hankel transform is a way to do it. And so this is just, if you go through it here, this would be the Hankel transform of this circular aperture. I think maybe we showed this before. I should, well, let me show this contour map here. This is a contour map then where we've added defocus to the spherical aberration. So spherical might go up like this, you know, it goes up as a rho to the 4th, and then the defocus is in the opposite direction, minus sign, and so the wavefront will go up and then back down. So in the center here, defocus goes as rho squared. Remember, rho is normalized to 1. So the center portion is mostly set by the defocus term, and then as we get out here, the circle takes over. And so the wavefront, as I put in this minus 1.5 rho squared, the wavefront here would go up like this and then back down. And this is where the slope is a minimum out here. And in fact, this contour line would be the same OPD as this contour line. So it may go up a little bit and then come back down. Anyway, we're going to calculate the diffraction pattern by doing the Hankel transform of the pupil function here. And if I just have spherical aberration, then the pupil function, well, it's a circular aperture, but the pupil function would just be e to the I 2 pi over lambda WO4O rho to the 4th. And if I put in some defocus, then the pupil function here would be e to the I 2 pi over lambda, well, WO4O rho to the 4th, and then we have to add in whatever the defocus term is. And so we can calculate these plots. So the first set of plots I guess I put here is where we have only defocus. We have no spherical present. So we would have our airy disk here. And then we have a quarter wave of defocus. And so the pattern looks like that, half a wave there. to where we get one wave of defocus and we have a 0 then on axis. Now if I do only third order spherical aberration, I would get something like this. Well, by 0 aberration, I get my airy disk again. For a quarter wave of spherical, I would get this. Half wave that, 3/4, 1 wave, and so on. So first I showed just defocus. Then I showed defocus in spherical. No, excuse me. And then I showed just spherical. And now I will show defocus in spherical. So this is where we have the same number of waves of defocus as spherical. And so, well, first we have no aberration. We get a nice airy disk. And let me go right to the last one here. So here's where we have one wave of spherical and minus one wave of defocus. Look at that. The peak goes way up there. While when I had just one wave of spherical, it looked like this. So defocusing can greatly improve my image quality if I have spherical. See that? So just spherical by itself, one wave would come way down here. If I add in minus one wave of defocus, it goes way up there. So I used to say that's what would save you. You know, when you buy your camera lens, you would defocus a little bit when you take the image to get a good image. Because almost every camera lens you bought had spherical in it. That's not so true anymore. I tell you, the camera lenses you buy nowadays are actually very, very good. But anyway, if you have a little spherical, you just introduce some defocus, and that helps you a lot.
Is that airy disk radii, is that normalized, or is it?
This is where the first airy disk goes to 0. So 1.22 lambda f number, however you want to think about it. But I just wrote that. I don't know what the I don't know what the f number is. I don't care what the f number is. I just write it normalized coordinates of airy disk radii. But the point I want to make sure everyone understands, I think you do, but if you have some spherical, now if I just kind of balance that with some defocus, I can really improve my image a lot. Okay, well before we go on to coma, let's go to my, see if I can find my website here. And I have this portion up here called Web Mathematica. And if I come down here, Seidel aberrations, point spread functions, that's going to be. So, yeah, what I have coming up default is coma. So let's get rid of our coma. We haven't talked about coma yet. And let's just put in a couple waves of defocus. So this is our contour map. This is our point spread function. And I picked the integer number of waves, so I got a dark spot on axis here. This is distance out here in lambda over d. If I had no aberration, the first 0 would be 1.22 lambda over d. And this is showing what the image looks like here. Maybe I should start off here with no defocus, just to look at that. So that's my airy disk. First 0 at 1.22 lambda over d. And here's the peak here. Peak to 1, first 0 here. I'll put in 1.5 waves of defocus. And contour map, point spread function. And now this peak is way down to 0.05 or so. I'll put in 0 defocus. and I'll put in 1.5 waves of spherical. Kind of a blur here, and that's little over 0.1 here, what the point spread function looks like. Now let's put in minus 1.5 waves of focus. Oops. So this is 1.5 spherical minus 1.5 defocus. So looks pretty good. And this is all the way up to 0.6 or so. So adding defocus to spherical, you can help things a lot. Anyway, you can go to my website if you like and play with this. Okay, so we're now experts on spherical, which is my favorite aberration. So let's now go to my second favorite aberration, coma. So coma here goes as W131. So it's going to have an off-axis. Something off-axis affects it. So it's going to be an X naught, a 3 there, so we have a rho cubed, a 1 there, so we have a cosine of theta. So on axis, coma will not be there because on axis X naught is 0. And it's going to increase in a linear fashion with off-axis position. And it's not rotationally symmetric anymore. It's not like spherical, it's not rotationally symmetric, so it's a rho cubed and a cosine of theta. And I can convert that into x and y pretty easily. So that's W131 x naught x times x squared plus y squared. Now I want to calculate the transverse aberrations, and this is a little more complicated, so I actually included the calculation here. Again, we remember that all we're doing, we're taking derivatives with respect to x and y. So epsilon sub x minus r over h partial delta w with respect to x. And x is rho cosine theta, y is rho sine theta, and so on. So we write down coma here in terms of x and y and x naught. And we take our derivative here, and so partial with respect to y, a little bit easier. We get minus 2 r over h, W131 x naught xy. And then I can plug in here what x and y are in terms of rho and theta. And then I use a trig identity here to find out that this goes as minus r over h, W131 x naught rho squared sine of 2 theta. 2 theta. Interesting. We'll see that in a minute. Partial with respect to x. Well, all of you can do that easily. So we get a term here goes as 3x squared plus y squared. And so I can write that, 3x squared and y squared. So I can write that as a rho squared here, and then a 3 cosine theta squared plus sine theta squared, and sine squared plus, I can get a 2 out of here, sine squared plus cosine squared, I guess. And I end up here with a result here of a 2 plus, I get a cosine of 2 theta when you put in the trig identity here. So both of these, x and y components, go as, x naught, which is not surprising, rho squared, and then a sine and a cosine of 2 theta. What in the world does that mean here? So that's just repeating what we had there. So if I think about this for a second, let's say my field point is fixed. So x naught is fixed. And let's say rho is constant. So I'm looking, what happens to the light coming from a region in the pupil radius rho. I see that we have the cosine and sine of 2 theta, so the image point describes a circle twice over as theta runs through the range from 0 to 2 pi. Okay, so as I go around the pupil once, the image is going to go around twice. It's kind of interesting. And the radius of this circle goes as r, well, W131 x naught rho squared over h. And the center here is just twice that away, 2r times, so on. And so if I look at what this image looks like, geometrically anyway, I look at what this image looks like. Well, first off, I guess I should have shown this. This is just the contour lines for coma. So these are lines of constant OPD for a given field point. But the image here, as I go around the pupil once, here's my pupil. I go around here once, this will go, I go around here half the distance, this will go around once. So as I go around this once, this is actually going to go around twice. And I said the radius of this, well, the radius of this in the image depends upon where I am in the pupil, but the radius goes as r over h, W131 x naught, so linear with the field, and rho squared. And the center of this is twice that away. So this is my radius, the center is twice that away. And so if I just use a little geometry here, this light, geometrically anyway, this light is contained within a 60-degree angle. Okay. And if we look here in the sagittal plane, C and D are coming there. A and B are coming up there. So we call this distance here the sagittal coma, and we call that the tangential coma. So isn't that kind of interesting? So maybe coma should be my favorite operation instead of spherical, because it's kind of more interesting than spherical. So maybe I'll change that. I'll make coma. No, I like spherical better. Okay, kind of cool. It looks like a comet, I guess. Well, let's see. So it turns out, when we had spherical, if we changed their focus position, introduced some focus, we got a better image. But that really doesn't happen in coma here. And even a lateral shift, it decreases the departure of the wavefront from the reference sphere, but it doesn't really improve the image. It's just selecting a different point other than the Gaussian image point to represent the best center of light concentration. So in testing, field position, we had an x naught there. And so if I were on axis, I shouldn't have any coma. But so many times in life I've been testing an optical system and I find I have coma on axis. And the real problem is that probably the optics you have are tilted or decentered or something. And so in real life you might see coma on axis. The other thing here, it's kind of interesting, remember coma was proportional to the field angle. So if I change the angle, if I change the sign of the angle of the field, I change the sign of coma. And so later we're going to see that maybe we can make use of that to cancel out coma. Okay, so let's go back here to the website. I think it's going to come up showing coma. So this is one wave of coma. That's what the pattern looks like. It's not rotationally symmetric, which we certainly see down here. And in fact, the image is shifted a little bit here. Let me put in a couple waves of coma. And you see what the wavefront looks like here. And you see what this looks like. So when you take into account diffraction, I mean, this is probably your 60-degree angle, okay? But when you take into account diffraction, you get these other kind of interesting interference terms here. And so you can't really neglect diffraction. I'll put in, just for a heck of it, see what 3 looks like. Okay. So anyway, that's coma, my second favorite aberration. So which one, if we were to vote here, how many of the two we've talked about, maybe some of you are going to like astigmatism better, I don't know, but how many like, of the two we've talked about so far, how many like spherical best? How many like coma best? Oh, coma is winning. How many like no aberration best? But then we wouldn't have a course, and so, you know, wouldn't have anything to talk about. So have I convinced any of you to go to a football game yet? Doesn't look too promising. How about basketball? I mean, I like football, but I love basketball. How many are going to go to basketball games? Okay, good. Okay. I'll forgive you for not going to football. But basketball you have to go to. Okay, astigmatism. Oh, I guess I have another drawing down here I forgot about. That's just looking at coma when we put in some tilt. And you can play with that on the website and see it pretty easily. How does this change as we put in tilt? Okay. Astigmatism. W222. X naught squared, rho squared, cosine squared of theta. So it goes as the second power of the field, goes as the second power of rho, and it goes as the second power of cosine of theta. And so we could write that as W222 x naught squared times x squared. And so if the way this works here, if I take a point source off axis, here's my lens. What I'm going to get, you're going to see in just a second, I'm a little ahead of myself, I haven't shown the transverse aberrations, but we're going to get two line foci. One will be in the tangential plane and one will be in the sagittal plane. And these will be separated by some distance. So geometrically, we just get nice lines here. If one takes into account diffraction, it's never quite that simple, but basically just lines. So the transverse aberrations, let me see here. I like this one. I can find the epsilon sub y pretty easily. I just have to take a derivative with respect to y and I get 0. So epsilon sub y is 0. And epsilon sub x then is just 2r over h, W222 x naught squared times x. And I could write that then as rho cosine theta. And I didn't show the contour maps, but we had no dependence on y, so this would just be straight lines in the y direction. It goes as x squared, and so as we get out towards the edge of the pupil, the contour lines are going to get closer and closer together, but straight, but not equally spaced. So anyway, these are our transverse aberrations. And I probably want to introduce some focal shift. And so I can add in a focal shift here. So epsilon sub z, h squared over 2r squared times x squared plus y squared. And then I take derivatives again. And now I get an epsilon sub y, and I get an epsilon sub x. And it's clear here, I think, that if I pick the right epsilon sub z, then this can go to 0. And so just like before I had a 0 epsilon sub y and an epsilon sub x, I could make it so it's the other way around. So that's why we get the 2 line foci. And so you can calculate quite easily what focal shift you need to get rid of the epsilon sub x. You know, maybe the best image is halfway in between. And we'll call that, again, the circle of least confusion. And what does the contour map look like at the circle of least confusion? Well, let's see. What we have is basically a cylindrical wavefront. So it's a plane wave in one direction and curved in the other direction. And now I'm introducing in a defocus term. And so what I'm going to do is probably to reduce this curvature. But in so doing it, I'm going to introduce a curvature in the opposite direction. And it turns out then for the circle of least confusion, going to be right in between. And so I'm going to have the same magnitude of curvature in the y direction and in the x direction, but they're going to be in opposite direction. So it's going to be like sort of like a saddle. You have a like this, and then the other direction it's going to go in the opposite. So concave, convex. Okay. And so at the nice to look at images of a wheel, spoked wheel. And so if I think here in the tangential image here, I'm going to have along this plane here, things will be in focus, but perpendicular to that plane, off axis, you know, say I have a point off up here. In this plane, things will be in focus, but perpendicular to that, they're going to be out of focus, going to be blurred. And so in this plane, the spokes here will be blurred, but the rim will be sharp. And if I go to the sagittal focus, then the spokes will be in focus, but the rim will be blurred. Okay, so okay, any questions? Sometimes this is a little hard to think about, but any questions here? Okay, and I have a couple of minutes. So we'll look at astigmatism. And where's astigmatism? I don't know. How much should I put in? 2 waves? I don't know. So this is what the wavefront looks like. And this is what the image looks like. So it's sort of like a line. I mean, you get a lot of other structure in here, interference, but it's sort of like a line. Now, let's put in minus 1 wave of focus. So here we got the saddle shaped, and here we got a mess. But that's a circle, so-called circle of least confusion. Okay, and X and Y slices, of course, look the same. Okay. So we've talked about my favorite circle. We've talked about your favorite coma. But I said, how about, does anyone have astigmatism for your favorite? Poor astigmatism. All by itself. No one likes astigmatism. Well, we're going to have a couple more things yet to think about. We're going to have field curvature when we come back bright and early next Tuesday. And we're going to have distortion bright and early when we come back next Tuesday. And then after that, we'll go on to Zernike's. So I'll see you all at the football game.